Okay, we're just trying to look at this question that we had from the exam paper. And I suppose when you're doing rates of change questions, it's really important that you look at every piece of information that you're given. So in this particular question here, you're given 250 centimeters per second. So centimeters cubed is to do with volume. So basically, obviously, it's to do with the volume of the sphere. And it's changing, so that's dv, and it's changing with respect to time. dv dt equals 250 centimeters cubed per second. Now, as we just mentioned, this is to do with the volume of the sphere, and we know the volume of the sphere. There's a formula for that: 4/3 pi r cubed. So they're the two pieces of information just from that very first sentence. And it's important that you write those down before you move any further. So you're asked now to find the rate at which the radius is increasing. So again, that's to do with differentiation, find the rate. So it's dr, and the question is what is that with respect to? In this case, it's respect to time, because it doesn't mention anything else, so you can just take it that it's time. So how does the radius change with time as time passes? And you think about as a ball is being pumped up, time is what's going to be important here. So we're looking for that. So at the minute we have dv dt, and we have this v with r in it over here. So if we differentiate the v equation, we get dv dr, because r is the subject and v is the name of the function, or name of the equation. So that turns out to be 4 pi r squared. So we have dv dr and we have dv dt, and we want to make dr dt out of that. Now, the only way for us to actually get that to happen is if we have these two pieces together, because algebraically, when you multiply those together, the dv on the top and the dv in the bottom eliminate, so we're just left with dr dt. So this is what we want, but what we have is dv dt. So that's fine, that second bit, but the first bit is the wrong way around. You can see we have dv dt, but we need it to be dr dv. So quite simply, you just take dv dr and flip it. And the way we can flip it is that if you think of 4 pi r squared as being all over 1, if we flip that, then the 1 goes on top and the 4 pi r squared goes on the bottom. And we're not, because we're doing the same thing to both sides, we're not changing the thing, we're just changing the look of it. And then you're just subbing in those pieces. Okay, and you have to, then you have to sub in your 20 that you were given in the question. So we have 1 over 4 pi 20 squared multiplied by, just put those in brackets, multiplied by 250, and that turns out to be 5 over 32 pi centimeters per second. And that is the answer for that one. Okay, we're here in question 7a part 2. Find the rate at which the surface area of the ball is increasing when the radius of the ball is 20. So find the rate at which the surface area. So surface area, so we're looking for the rate at which the surface area is increasing with respect to time again. So dA dt. So we're looking for dA dt. From the previous part, we found dr dt. So we need something else with a in it. So again, we know that we have a formula for area, surface area, is 4 pi r squared from our maths tables. If we differentiate that, we end up with dA dr, which is 8 pi r. Now, if we just combine the pieces, dA dr, if we multiply that by dr dt, we would get dA dt, because algebraically dr dr would cancel and we'd be left with dA dt. So then it's just a matter of subbing that in. So we have 8 pi r multiplied by our answer from the previous part, which is 5 over 32 pi. And when you trash all that out, you get 5r over 4, 5 times 20 over 4. That leaves us with 25 centimeters squared per second. And that's the second part of that.